So I'm really happy to have Dr. Penelope Boyden with us. And this is not her first visit with us. And we've known each other for a very long time, I think. I don't remember when was the first, but I used to visit Columbia University in the Department of Pharmacology, where Penny is, many, many times in the past. So I don't want to make it into a long introduction, but Penny has done a tremendous amount of work in the area of cardiac arrhythmias, cardiac electrophysiology, and she's a professor at pharmacology at Columbia, and early on worked with the legendary Brian Hoffman.
One who writes legend for that.
Legendary.
One about whom.
There are three legendary people in cardiac EP. Those who know who they are, it's a quiz. So anyway, she's been working on isolated cells, looking at the cardiac electrophysiology of isolated cells, both Purkinje and ventricular myocytes, with emphasis on cardiac infarction, remodeling post-cardiac infarction, myocardial infarction, and they did some remarkable work on the border zone of myocardial infarct, where many arrhythmias reside. So without
Thank you very,
further
very much,
statements
George.
here, thanks for coming.
Yeah. Well, it's been very, very nice day to see you all here and to talk to you early. And I see that there's a group of graduate students, I assume, back there. I will ask you to ask questions at the end before the grown-ups, okay? If you don't mind, so keep that in mind. As Yorm mentioned, one of the projects in the lab is working on cells that have come from hearts that have disease, and we use an animal model of disease and all. It's in the dog, where the coronary artery is occluded. And it has a progression, the infarct. There are arrhythmias right away, and then there's a quiet period for about 18 hours, and then there's a series of arrhythmias at 24 hours that come from the Purkinje system. And then if you wait till 5 days, what we call a healing infarct is where you can stimulate the epicardium and actually get reentrant circuits. So to focus today, I focused on the sodium current in these cells that survive in the infarct. And the sodium current plays a very important role in particularly in the epicardial border zone, which is the ventricular cells. I'm not going to really talk about the calcium work in the Purkinje cells that survive the infarct today, because that's like a whole nother thing, but to focus down on the sodium current function. What we found, and a lot of this has already been published, but what I'm going to show you at the end is new and builds on what we saw in the past. So I'm going to try to get this moving. So essentially, in the epicardial border zone, with an extra stimulus technique at the right place over where there's surviving myocardium, you can get a monomorphic VT. And now I got the wrong one. Go back. And what I'm going to show you is that we're going to work through all these different parts of the experimental model. And then we have some in silico data where we try to model the reentrant circuit based on what our recordings of the ionic currents are in the individual myocytes. And you'll see that. Now this work, I have to start out with my mentor Andy Witt, who is not like Ron Hoffman and Nick Peters. They did a lot of work. And this just shows a series of isochronal drawings that they mapped with just an epicardial plaque placed over the border zone. Here's the LAD. And you see that there's a reentrant circuit, some people call it a figure of 8, where there's a central common pathway, and there are 2 lines of functional block here, and the circuit can maintain, and these are sustained VTs in this model. And they were quite obsessed with connexin 43, and I don't know if everybody knows the story about connexin 43. This is not what I'm interested in, but obviously when Nick, who did the connexin labeling of the border zone cells, noticed that the connexin wasn't where it was supposed to be. It was at the gap junctions, but it was also all around the sarcolemma. So this redistribution of the connexin protein made this an even more interesting model and said to me, well, there has to be something else going on here. It can't just be connexins moving. And what are the other currents that could drive this? And you'll see we've done a lot of the currents here, but we're going to focus on the sodium current. So I want you to remember that this is the central pathway, and this is considered outer, and they're on either side of the line of functional block, which is pretty consistent in one substrate, one heart. Okay, next one. So to begin, we're going to talk about myocyte experiments, where with a very fine grid, we actually mapped the conduction velocity first in the normal heart, and you see we have a faster longitudinal conduction versus the transverse conduction, which is normal for a normal non-infarcted epicardium. And this conduction can be measured from these 312 sites by using the vectors. So you have a transverse vector for this kind of conduction and a longitudinal. And this gives you an idea from the work that Andy and Nick had done that this pattern of longitudinal being faster than transverse is normal in normally coupled connexin 43 cells, and then it changes a little bit when you have an infarct. So this is the way we started with the mapped myocyte. We first mapped and got our vectors. In the outer pathway, you could see that you still have surviving longitudinal conduction velocity here, and there are numbers here. But the transverse is much slower in the outer pathway of a 5-day infarcted heart. And then we micro-mapped, because it's 312 sites instead of the 25 sites that Andy had done. We see there's, again, still a very robust longitudinal conduction and a slowed transverse. So both pathways were recapitulating the general pathway, but remember, one served as the outer pathway of the reentrant circuit, and one was part of the central common pathway. So in summary then, the central common pathway was where Nick and Andy defined the connexin lateralization around the myocyte. So we have connexin lateralization, and there is a reduction in the longitudinal, and a reduction in the transverse conduction. This is transverse conduction longitudinal. In the outer pathway, there's no lateralization of connexin 43, and we still saw a reduction in transverse. This is the normal value for our transverse conduction velocity. And then 45 is no difference between 37, and there's no lateralization. So you can see right away that there's something about the remodeled cells in the center pathway that differs from the remodeled cells in the outer pathway. They have different anisotropic ratios, they're longitudinal or transverse. So the mapping experiments led to first making single cells from the same heart on the central pathway and one of the outer pathways, and the dotted lines were put here, and this would be about the size of the piece of epicardium that was shaved off and put in to be made into single cells. And then immediately opposite that, in the center pathway, you took another common shave, and in a double titration, you could make cells from both sides of the line of functional block at the same time. And we had all the rigs going, because there were a lot of cells to study, with the idea that there were subtle differences between the ion channels here versus here that led to the line of block. We couldn't find fibrosis leading to the line of block. We couldn't find edema or anything like that. So there was a possibility that there were differences in the ion channels between, very subtle, but between these two different populations of cells. And here you see a typical action potential from a normal heart, normal border zone heart, NZ. It has a rapid upstroke, a nice notch in the epicardium, square. It's very identifiable as a normal cell. And here you see a typical IZ cell, and when I write IZ, that means infarct area. There was no distinguishing, in other words, we hadn't mapped the epicardium first, so we didn't know what the central pathway was or the outer pathway. And you have a reduced upstroke. Good resting potential, suggesting there's a sodium channel lesion here. And this usually looks like a bubble membrane, and the gap junctions are okay. They're not always the best at 5 days. This membrane is full of what looks like a lot of lipid droplets. And I've never gone on to find out how the membrane changed. So we have center pathway cells and the C outer pathway cells. They were studied on the same day, same conditions, same time after whole cell membrane rupture. All the rigs, 3 rigs were working the same. The rundowns have to be the same, and that was very important when we were recording the sodium current in these cells. Obviously the solutions were same. And then some of the cells were fixed for cytopenia, looking for the structural model. And this is an overview of the results. That first, the density is decreased in both the center and the outer of the sodium current. But you see there is some overlap, suggesting heterogeneity in both populations. And the capacitance is not really that different here. But you see there are kinetic differences between these currents, between the center and the outer. So when you look at the kinetics, they're actually quite interesting, that the outer pathway is slower here during the time constant of decay of the current, okay? And the time to peak is different. So this will become important when we put it into the cell model, that there's a small kinetic but significant difference. So in the outer pathway, which remember had pretty good T to L ratio, the time constants of the current decay and time to peak are larger than those in the center pathway. Perhaps this is the distinguishing feature that makes them different. I think more importantly were the curves generated for availability and inactivation for the sodium current in isolation. We see a shift such that not closed state, I've been talking to you guys too long today, the center pathway cells are shifted to the left, and this inactivation curve is no different here between the center and outer. So those small differences in kinetics and the decay were then modeled by Candido Cava. On an aside, in another series of experiments, certainly not on the same day when you do sodium current measurements, we actually did the calcium currents, and we find that there's no difference in the calcium currents in the center between these two, but they're all different than normal with a depression. And that'll be important because it had to be added to the model. So we have a summary here. Now, the interesting here, the only thing that we found different kinetically is that the center pathway calcium current has a faster decay. And that could be important in terms of the time course of repolarization, and we'll see that in a minute. So the idea was then to develop an in silico model and see whether either of these together or separately, yeah?
How long after the infarct was this?
5 days. 5 days
Do
is
you
when
know
you
if
get
it
re-entry.
Does it matter? Did you do anything, before 5 days, or
Well, I've done a lot before 5 days. 5 days is for re-entry and excitation, which has 2 functional lines of lot. And the question is what maintains the line of lot. Later on, the infarct evolves, and there's scar tissue that's forming, and it becomes a reverse remodeled substrate. Okay, now it's not exactly normal. The action potentials are a little shorter by 14 days, and then they go all the way out to a month, and they look normal, but I don't think they're normal because they have a huge sodium current in the plateau. So there are different phases and timing. The most arrhythmic part of the dog is in this 24-48 hour period, which is due to the Purkinje virus, and then this inducible reentry, which you can get from any premature. But good question. Okay.
Penny?
Yeah.
That low threshold current that you're seeing there, is that the sodium current that's residual, or is there a
No, I
T
think
type?
that's a calcium current, right? This one?
Yeah.
Yeah, I think that's calcium. T, it's not a real T, But I've seen T currents come in ventricular cells when there's a change in, there's stress in on the cell from diabetes and stuff like that. And also developmentally, I think there's T in ventricular myocytes. Okay, let's go forward. So in the model, Candido Cabo started with Luarudi and then no intracellular calcium, of course, at this time. We weren't thinking that way at all. He has the IVs, the kinetic, whoops, the kinetic information for the center and outer for the sodium current, the IVs here. And you just look at the action potentials and they don't look any different between center and outer, right? But you see here that the APDs are relatively the same, but the ERP is different. So recovery from activation is actually slow, particularly in the center, right? Upstrokes are no different, velocities are no different, and that's when he actually made a strand of them and actually measured the conduction velocity of a strand of these myocytes. That's with sodium current differences only. This is with calcium differences only. And they actually he showed that the outer pathway is a little longer and the ERP is a little longer here too, and DVT is more. So the question is, are these differences by themselves enough to make a line of block, or do they have to be combined together to make a more stable line of block? It's the idea of understanding what causes the line of block makes you want to go into, well, what antiarrhythmic or what drug could you give that would terminate the arrhythmia by dissolving the line of block, okay? So this is the kind of model he had, and I didn't have the drawing of the array, but he had several 300 array, and he could actually get a movie of it. And I'm just going to show you the catching of the last 3 or 4 episodes in this run. All right. 1 and 2. Oh, I'm going backwards all the time. Yeah. No. Here you see 1 is right at the line of block, then 2, you kind of see this, and then 3. So it's still revolving around this fictitious line of block, just the differences, and then 5 and 6. So I didn't tell you what the differences were here. Was this just incorporating sodium current differences? Is that why you got a sustained line of block? Was it just the calcium current measurements that were different in the cells and the ERPs were different? Well, in fact, if you plot them all together, you see that when you have included in the model of the action potential, sodium current and calcium current changes between the center and the outer, you get the most stable line of block. When it's sodium current changes alone, you have a couple of beats, but that wouldn't be sustained like it would be in the real experiment. And the calcium current alone obviously terminates itself, probably because the action potential is longer here between the two. So clearly, it's a balance of the sodium currents and the calcium currents that helps maintain the line of block, at least for these beats here. Now I have to tell you that this model that I've shown you with Condino is a very thin one-dimensional model. It does not bring in the structure underneath the info, which Andy had gone on with other modelers to show is an important stability factor for the VT. This is just a thin two-dimensional model. So, also you come away with thinking, well, the repolarization changes that we saw between the two cells didn't seem to be a factor. And it's the heterogeneities between sodium and calcium channel actions that lead to stability. And this is the rationale for looking for a better mousetrap or a better anti-arrhythmic. And there are a lot of things to think about when you're trying to restore something or put them back. We don't have good sodium channel agonists. We clearly have good calcium channel agonists. And interestingly, BAG-K did stop the arrhythmias. Andy was not mapping at the time when they gave it, and there is a problem with it also having a vascular effect, so it wasn't useful data. We needed a cleaner one. Replenishing subunits. If there were it was a mismatch of the subunit, the minor subunit with the alpha subunit, you had mismatch of subunits and you flushed the system with one. And this came to my brain because of the K-chip story that we were hearing about K-chip recovering ITO in cells that were lost to ITO or something. Or just adding alpha subunits back for rescue. And Mike Rosen actually went on and tried to use skimmed sodium channels and add back and see if they could substitute for the cardiac channel with skim. And I'll show you that in a minute. So here was our attempt to try to recover sodium channel function with using pKa. pKa had been shown by Kathy Murray in a series of experiments, not in myocytes, that it would promote trafficking of the sodium channel actually to the membrane. And we did have an effect of pKa on the normal, small, and a very small one on a very sick borderline cell. I wouldn't say it's a real winner. There is some recovery, but I don't know if that would be anti-rhythmic. I don't know if that would break through the line of loss. So this did not prove to be a very helpful. It could be in addition to something else, a massive pKa. This was done with 3 different things that increase the amount of activation of pKa in the cell. So it was pretty disgusting. Replenishing the subunits, and here I never could get the beta one, so we tried, for instance, just proof of principle using the K-chip to bring back the ITO, which is in fact gone also in these cells, and it was very effective, so we thought it would really work. But K-chip didn't do anything to the sodium currents. There had been at that time a publication that suggested that maybe K-chip also helped the alpha subunit of the sodium current back, but it didn't do anything. So it didn't look like we could rescue by just, we needed more knowledge of the subunit that we needed and needed a better vector. And again, it was very difficult to do these experiments because you had to inject the vector with the, before you actually produce the infarct. So you had to sort of guess where it was and then make sure that you had your VT there. So the last thing was, Mike Rosen with Rich Robinson's help did the sodium channels from the skin, and I'm not really a firm believer in the data, but it showed that they could get expression of the skin channel in the cells by putting a GFP with it. These are very TTX sensitive, but in fact, and you could see but their cells don't look very borderzone to me, so they were getting something somewhere, but I wasn't sure whether it was in the center of the outer pathway to actually stop the arrhythmia. But they actually did some pacing and started the arrhythmia. This would be a typical ventricular arrhythmia that would come in the border zone of a dog, and they got that in their GFP animals. And then they had the animals that they had actually gone around and every 2 or 3 millimeters injected skim and then let it set, and then came back and made the infarct. And they actually feel that they had success here. So 1.4 was then blotted, and they could see that it was being made by this cell, which doesn't look like a borderzone cell. So this was working, but I'm not sure it was totally convincing to me, and it's because the effects here on longitudinal velocity is not very great. So even the infarct hadn't produced really dramatic slowing, right? So they weren't really working with a really slowed, sick infarct, and that was where I was recording the sodium currents from the sick cell. Anyway, so the problem is, what else could be successful? And you don't want to give a lot of drug where you're just trying to target the reentrant circuit, right? I mean, we do that anyway. I mean, we give flecainide because we want to get atrophy, but we want all of the substrate slowed down with flecainide. So I think that we needed to step back and think about other things that were going on in the infarct cell and ask, well, are we really trying to recover something that just can't recover because the intracellular machinery is not there, right? Okay, so maybe the alpha subunits aren't there and the beta subunits aren't there, but is there a way that they can traffic properly? So we slowly got into this part of the field, and I think right now we don't really still have the right tools to restore full excitability, but the goal is either to restore the sodium current function or the calcium current function and get rid of the line of block. So off we went to look at trafficking. Now, you all know Robin Shaw, and you know he's been working years on trafficking of the connexin protein. And to the best of my knowledge, and anybody here can correct me, I would love it, the sodium channel trafficking is not well worked out, okay? But we can guess that there were going to be some fundamental similarities between what Robin notified as targeted delivery of the connexin protein, where you have cargo leaving here from the trans-Golgi, getting with its partner, chaperone, and going on the microtubule, and then with its protein EB1 identifying a site where it can actually deliver the cargo to the sarcolemma. And in this case, deliver the cargo to their catinin and desmin, and this is for connexin 43 in the gap junctions. Now, of course, we all know sodium channels are also at the gap junctions, but the question first is, it's doubtful that all these proteins are involved in the sodium channel trafficking because it wouldn't be specific. But there are some things, some proteins here that are probably common, and the first one is the microtubules. Now, microtubules, we all learned that way long ago, and we learned that they had an important function. And slowly, it's come into the literature that if you polymerize the microtubules, then the cell will lose its sodium current. In fact, there's been a couple of papers in the last 5 or 6 years. So it was the first place for us to start. Okay. And there are some other molecules here we'll talk about. Oh, no, I put anchorin first, sorry. Because I was working with Pete Moeller, he was more interested in, and it's actually quite interesting the way it worked out. Unlike connexin, over here with, let's say this were a sodium channel going into the intercalated disc, there would be an anchorin protein, and I think I talked to some of you today about it. And that anchorin protein would be connected to a spectrum, and that gives rigidity of where the location of the sodium channel is at the gap junction. And it also is along the sarcolemma here. So the first thing we did was see, because we knew the sodium channels were diseased, was there any problem with the anchorin? Maybe the anchorin went away, and that's why they don't stay in the membrane, okay? And here he shows very nicely that the anchorin is here, and the ion channel, or the other protein that faces outside, is here in the membrane. And there's this big structure, spectrum underneath it. But anchorin G is the one that likes to target sodium channels to the cardiac membrane. And dysfunction has been defined by Peter in this pathway in a Brugada syndrome with a mutation. So the idea was that if this is, we don't want to have it mutated, but we wanted to have it, we wanted to see even if this was changed with the infarct first, and then see what kind of change it was going to be similar to being gone. Here was some of the early staining for the sodium channel of these cells, okay? This is not center and outer. This is normal, and this is a surface slice in the confocal, and this is a subsurface slice. And this early antibody shows very robust staining along the sarcolemma and at the gap, which we now know with Mario's work and how that's formed. And then also on the sarcolemma we had a signal. And this particular center cell lost most of its channels on the sarcolemma, but saved the channels on the ID. Okay? So that was interesting, but we couldn't quite understand this as we first saw it. Here's another sodium channel of a remote cell. And remote cells are normal area in the infarct that wasn't involved, more over into the right ventricle. So it's like a sham control. So it's away from the infarct and it's called remote. And they look normal, but clearly from an infarcted heart. And then from this particular heart, we also had a 5-day cell. So this is a 5-day with sodium, and that's sarcolemmal staining and an intercalated disc. But here's the ankyrin in the remote, and here's the ankyrin here. Intense staining on the sarcolemma. And that was quite unexpected with the fact that the sodium is down, the sodium density is down, yet it appears that there's an increase in the ankyrin right underneath the membrane, and particularly at the disc. So we needed more proof of that, so we had expression data done on the sodium current, on the sodium alpha subunit, and the 190 Ang-G expression. And as the infarct progresses, 24-48, and here's the 5-day, you see a reduction in the expression of the cardiac sodium current, but an increase in the expression of ankyrin. So the ankyrin, we think, is somehow trying to stabilize everything, or with the spectrin, trying to stabilize everything to stay on the membrane and not be lost and loss of function. Here are single cells done more recently in a better confocal. And what you can see here again is this very nice lattice pattern of the sodium current, and this is a Purkinje cell, and the gap junction here. And then when you merge them, you can see that the ankyrin and the sodium right here overlap, not necessarily on the surface. And then the infarcts are here, and we see this dense staining for the ankyrin. So there is something that about the infarct that stimulates the expression of ankyrin to try to probably save the cell from curling up. And again, we had frozen tissue from this. These are Purkinje fibers again from the infarct, and this is a 48-hour infarct. And we have the same relationship where there's a thickening of the ankyrin here in the infarct area as the sodium currents are going down. And here's a normal sodium current. So ankyrin I don't still understand what's happened, but you'll see that there are other things that go up when we thought that they would go away. So they seem to be responding to the an increase in protein availability.
Maybe it has to do with the lateralization of the gap junctions. Because now you have ankyrin all around the membrane.
Well, you always have ankyrin all around the membrane.
Like
No, not solid.
I don't know, it's just an hypothesis.
So ankyrin is hanging on the sodium channel. It should be normally, and then spectrin. And what you're saying is because the connexins move, that the ankyrin will respond to that by building off the connexins. I don't know if I've ever.
I don't know enough about the trafficking.
I don't know if
sodium
ankyrin
channel,
G goes to connexins. I think it's specific for sodium channel. But there might be a common thing for spectrum.
Sodium channels are expressed on the intercalated discs.
Right.
So maybe with the lateralization, I forget that, just a guess, has something to do with it, because it's not independent. It
Okay,
changes
well,
the whole.
so let's go back. So Andy always called it lateralization, or Nick did, right? In fact, is it really lateralization? Because I think that these don't move. This is Robin's work, right? Connexins. What they show is that there are more connexins here than there were than in control. It doesn't mean that these actually lateralize.
No.
This means that the sarcolemma now becomes the target. So it's a miscuing of the targeting, right? In interpreting what he's showing here, right? That somehow there's a miscue and the connexin will go to the sarcolemma as well as the LD, right? So you think, well, it's possible that that then sets up an ankyrin reaction. But I don't, that would be good to.
The longitudinal conduction velocity also goes down.
Yeah.
So is it lateralization, or do we know whether it is in fact
We don't.
being redirected? Because
No.
you know?
I don't think we know unless you really tag the different.
Right.
I mean, those things come to the membrane and then they move.
Right, but I guess the thing is there more per cell, or, and it's just mislocalized, or did the total amount?
For connexin?
Right.
I don't know that data. To me, it looks like there's more, but it could just be misdirected because there are an awful lot here that you'll have to ask for. But the sodium channels, there's a reduction, and a reduction sarcolemma is more than at the disc. So-
The function of the lateral ones, the connexin, must be the gap junction.
Yeah.
Must be compromised. They can, right, because the anisotropy ratio is increased.
Right.
So they conduct less.
They conduct less.
There are many of them, more of them, but they conduct less. So, who knows what's going to happen.
Okay, so, the anchorin that would be here next to a sodium channel, and the spectrum, I'm assuming we didn't do that yet, and the ones here, it's thicker, and we don't know if it's changed the way it's built, or if they've clustered, or the spectrin has brought in a clue for them. So now we get to the microtubules. So these are really important structures, as I'm learning, and they're, as I mentioned, there have been reports that protein expression is decreased if you polymerize them, and this would reduce, obviously, the current, and that you need correct microtubular function to have good phosphorylation of the sodium current. So remember I showed you in the first slide, we were not able to really bring up a lot of sodium current functionally with phosphorylation, so it could be the reason. Although, now, I don't know if you can see these. So this is a remote cell from the same infarct as this one, 48 hours. This is from the border and there are no reentrant circuits, so this is not center or outer. This is just asking the question, what's the microtubular status in the infarct? And you see a lot of the characteristic pathology of microtubules here. You see a clustering here around the nuclei here, along the tip of the cell. There's disorder. It's not linear here. You can see them. This also has a transverse. And I really didn't like this slide, so I made this slide. This is the whole network in black and white with all the images of the Z-stack. And you clearly see the microtubules going transverse because they have to get their cargo also to the sarcolemma, as well as going along the cell. And you do have a densification. And this is a remote cell around the nuclei. You'll see the nuclei will show up here. And this is the infarct cell that you saw before. You see this sort of spiky polymerization and aggregation. You see them, they're not straight anymore, they're disconnected, broken up. So it becomes a set of, and Robin calls them highways, a set of highways that have a lot of need for repair. Good budget.
So the polymerization means they become more disordered? Or?
They stick together, they aggregate, yeah. And now
And what causes
you're right.
that?
I don't know. I don't know what causes it. It's as early as 3 hours. I'll show you that in a minute. But essentially, they're not as, myocytes aren't, they're stiffer, right? Because there's a lot of this right under the membrane, right? Now, I chose to, let's find out this, so that makes it a very stiff myocyte. I chose to, an example of a 5A, slides 8 and 10, same cell, and a 3-hour infarct. I started going earlier because I wanted to have the polymerization. I wanted to see when it was changing, and was it reversible, right? So this is just 3 hours of ischemia on the heart, and you could take out the Purkinje. And you see your loss of the microtubules, but you do see some that are still going transverse, particularly in this gap junction area. And here's a little aggregation. Here's a rather larger aggregation. So clearly, there are pathways to get to the intercalated disc, and pathways less so for the sides of the cell. But they're not, they have a different dimension. They're usually thicker. I did not measure them. And work by, I think it was recently about the growth of microtubules. And just as Robin had shown, the EV1 is important to target them. That doesn't work in this dog. But they add on, and it's usually targeted because they have some clue as to where they're going, some biochemical clue. So they have hope that they could maybe repair from this, right? So one of the things that also worked on with Peter was this protein called EHD4. These are EPS15 homology domain protein products that are intracellular proteins, and they are appearing to be key to trafficking a lot of the membrane proteins we're talking about. And he had done some work with Jeff Curran on the calcium channels in the transporter, and he found that EHD was like the carrier of this other protein and helped it get to the membrane. So I naturally said, well, which EHD is important for sodium channels to get to the membrane? He said, well, EHD4 binds ankyrin, so EHD4 bound ankyrin should be important maybe for bringing the channel up to the membrane. And in fact, when we looked at just arbitrary units of expression of EHD 3 and 4 in the remote slab or a border zone slab, this is a 48-hour infarct, and this is a 5-day. You see that EHD 1 and 2 are pretty much similar, but 3 pops out by 48 hours and becomes robust. 4 is still quiet, okay, but still there is some. And ANC-B is related to EHD3. In the 5-day infarct, you see 1 is up already, and this 3. So they're all busy carrying their protein or helping their protein of interest get to the right place. So in the 5-day, you have 3 and 4, and 4 is robustly increased. So we started looking at the relationship between the tubules and 4, because how would these EHD4 help its cargo? It needs to have a pathway, and so one of the pathways would be this tubule. So we co-stand with the microtubule and the EHD4 green from the here. And again, we see EHD4 in the normal or remote cell has a very specific lattice staining, and it's along the membrane, and you'll see more of that later. And then inside, in the core slice, it's relatively heavy around the nucleus, but you'll see it gets worse. This is what happens in the 5-day. So in the surface, this means the first plane that you take with a confocal, not the very top, but the next one, so you're getting, I don't think you're getting sodium channels, but you're getting what's just below them. This is not sodium channels, but this is microtubules. And you see they're widened, and they have a lot of the EHD4 in them. And it seems to still be longitudinal, and there still seems to be a highway there, but it's a little bit chaotic, particularly up here near the gap and down here. And then in the inside of the cell, we have heavy co-localization of the two. So this is where there's the gathering of the EHD4 with its ankyrin or with its sodium channel or whatever to actually get on the way to deposit the cargo, I think. And again, this is a blow-up showing this lattice thing, and it turns out that EHD4 can bind right under the lipid bilayer and be quiescent, and then with stress, it changes in configuration and becomes released from the lipid bilayer. And that was shown for EHD2. It has the same basis in EHD4. And again, you see a higher gain. You see the sodium channel, this is not sodium, sorry. You see EHD4 and the microtubules. And they're very linear. There's some sort of organization there. But I'm shocked that not all of this is microtubule. So the EHD4 has a plan on how to help get its cargo to the membrane, but it doesn't always need microtubules. So this could be retrograde, and one could be retrograde, right? I don't know. And then this is really a very sick cell because there's not much in the inside of it. So to do anything quantitative here, of course, you have to look at a lot of cells and get them either on the same day or within 2 days in the scope, and then make the same ROIs and things, and have the remote be your control, and then the co-localization area of the two proteins, and you see there's a stepwise increase of the Ph.D.4 with the microtubule, so more there. And here's the surface plot, which I showed you showed a lot of staining, and it doesn't get significant until 48 hours. So here is again another contrasting the Purkinje cell at 3 hours, and you still see a lot of Ph.D. 4 along the membrane, and you see the microtubules there, and there's not much at 3 hours, but the microtubules look pretty normal here. But here at 5 days in the ventricle cell, you see this quite organized activity between where is the Ph.D. 4 and it's in the microtubule. And again, I was a little bit shocked that there was a lot of Ph.D. 4 and a nice linear line here, and I don't know what's carrying it or where it is. Is it still bound to the membrane maybe? I don't know. And perhaps most interesting was this series, because I just showed you that at 3 hours, the microtubules aren't really that sick. But at 3 hours, we saw Ph.D. 4. This is slicing starting right at the top, so you don't get anything here because you're not even in the myocyte. You see lots of globules, and that, I think, is being released from the lipid bilayer. And then you go down, and you see the microtubules. They've thickened around the nucleus. And when you look at the high power of this one, you see that there's septum now in the nucleus, and sometimes you see that even in normal cells, but there's a lot of Ph.D. 4 in the nucleus. So the cell is like unloading its Ph.D. 4. Part of it is traveling up the microtubules, and part of it is coming into the nucleus, and we don't know yet what it's doing. In fact, at the 48 hour, in another animal, but the Purkinje, it's a rather large orb of these collected Ph.D. I think they must be diamonds. They're so big. It's not just one. So we think there is a transcription role for the Ph.D. 4 in addition to its busy work taking cargo to the membrane. And it's using the microtubules. So the question is so there's a large amount of Ph.D. in the nuclei, and that's leading us to the idea that it's involved in the transcription. So it has many roles in the cell, and it's important because it's specific for at least one ion channel that we know about, the sodium channel. So what happens to the sodium channel? So this is the sodium channel alone in the normal cell, and again, this is a normal heart, not a remote heart. And you see the patterning, and this is a subsurface slice, so you see right along the membrane and right underneath. It seems organized in these longitudinal stripes, like the Ph.D. 4. And we see the infart at 48 hours, and this is a border-zone infart. Again, there's still some organization here. They're a little bit closer to the, I wouldn't call cluster because Mario's not here, but the presence of the channels seem a little closer together in this infart. But when you put it together with the microtubules, in the core, first you see the remote will have both Ph.D. and sodium channels, and so will the infart. But look at all the Ph.D. 4 left over in the core. That must be doing something there. I don't know what it's doing. So it could have even another function rather than helping cargo go to the membrane, like this particular microtubule in the Ph.D. 4. But more interesting are the surface here. It's overlaying in the remote, and then you have these very large highways with a lot of Ph.D. 4 and the sodium channel. So I think that the Ph.D. 4 is actually the driver here and will be the key to promoting the trafficking of the sodium channel. And whether the beta subunit helps or is needed for actually, this is a sodium channel alpha subunit, but are there also beta subunits that line up with it, or are they on the way and they grab them and just before they insert into the membrane, they get it together. And again, the colocalization wasn't statistically significant on the surface, but there was more in the core, as you can see from the picture. So the sodium current, or the cell location, is altered early after coronary occlusion. A portion of the sodium channel uses microtubule networks, which are certainly altered in the post-MI cells. And a bit of the sodium channel protein is within the nuclei. I didn't show you that data, but there's a large amount in the perinuclear area. So I think for targeted delivery of the sodium channel, we have a lot to understand here. We don't know what our EV1 queuing at the top of the microtubule is. That lets connexin know that if they're about ready to get to their stop and they need to get off and bind to their catenin. So we don't really know if this is non-directed targeting, as Ron has written here, or is it both non-directed and targeting with a microtubule. We did see transverse microtubules with sodium channel or sodium antibody in it. So this is sodium channel recovery. Which part of this targeted delivery would you actually target it to see whether you could augment or be an agonist for the sodium channel? And it seems to me that it's getting very complicated because sometimes proteins don't do what you think they should do. For instance, I thought ankyrin would go away and that you could put ankyrin back in and maybe the channel would actually stay on the membrane, but that wasn't what we found. And I don't think that we know how to promote the sodium channels to get into the microtubules to actually facilitate trafficking. So we have a lot to learn in this particular aspect of our sodium channel field, or at least in the cardiac side. Okay, thank you very much. And I asked the young people in the back to generate a couple of questions first, please. Thank you.
Questions and comments?
They're shocked. Yeah.
Very interesting. So it's really cool to see that sodium channel during the remodeling. So one aspect of this, the current density goes way down.
Yeah.
So that's traffic aspect of it. The other thing that you showed was the actual characteristic of the sodium channel is changed. So I
The
was wondering-
kinetics, you mean?
Right, like the
Yeah.
activation and inactivation
Yeah.
curve. So I was wondering if you have any idea of what's causing the changes. Because if it's just a pure trafficking issue, that wouldn't lead to a change in the activation and inactivation.
No, absolutely not.
So what do you think might
Well,
be causing that?
one of the things, I think we talked about phosphorylation of the channel and trafficking, and in the early experiments, we tried to bring up channels by phosphorylation based on Kathy Murray's work. So that certainly is one aspect that could shift the activation curve, right? And we did not, because this is such a little amount of material, it's extremely difficult to actually pull down the phosphorylated form versus the non-phosphorylated, And so the idea was to see if there were differences functionally that could account for the line of block. And we found that there were. Now you're asking is why were they different, right? And it's not targeting. I think it's a good question. I had done the PKA before finding out that this was shifted, so it just reminded me that it was a phosphorylation channel. So it's probably phosphorylation, but I can't tell you for sure. Okay, other questions from everybody? Yeah.
Anyone?
It's kind of related to that question. I was wondering, since you have I guess difference in microtubules, would that change the mechanical environment of sodium channel that since they're mechanosensitive?
Absolutely. Calcium transients, sarcomere shortening, everything is very rigid in these cells. Very rigid. They don't contract. 5 days. If anything, it's just the tips that contract. hemiphasic, right? So, but that's at 5 days. So the real question is, when does that start, and could you prevent it from actually getting so stiff? So you would say if they're stiff, when you want to recover activity, you shouldn't have the microtubule problem, right? So how would you stop that, right? But maybe the cell needs the microtubule polymerization and the lack of movement in order to get new cargo to the membrane. Huh? I don't know. It's a very, very large portion of the inside of the cell. Microtubule. Yeah.
Does nuclear membrane have ion channels or
Yeah.
do they transmit high voltage?
Oh, I don't think they have voltage, but I know they have channels and IP3 receptors and things like that. How does EHD4 get in there?
Well, what are the ion channels for on a nucleus?
Probably for some signaling problems, right? A lot of signaling. The other thing on that, from the microtubule, I don't know if microtubules actually go into the nuclei. Probably not, but they probably come up right next to the envelope, right? And then they can bring whatever they are to the envelope, and then that somehow gets in. But I don't know much about the transmembrane voltage or trans over nucleus. Do you, Gene? I don't think anybody's wondering.
But you're asking whether there's voltage-gated channels in the nuclear membrane.
Yeah.
Or channels.
But I think
Channels
what she
are
was
voltage.
showing was just staining for the protein inside the nucleus.
Oh.
Yeah.
Not on the node.
Not on the
No.
membrane. Yeah. So in other words, going through
And
the
then
nuclear
it
pores
gets in there
probably,
and forms
yes.
an orb of some sort for some reason. But EHD2, one of the isoforms, actually has been shown to control transcription of the protein that it's in charge of, right? So they have a self-fulfilling thing. We don't know yet whether 4 is in charge of controlling the expression of sodium. Yeah.
So I was wondering, with our channels, we want to increase expression, and we got rid of the ubiquitination of the C term. So I was wondering if you had looked at
No.
whether maybe they get recycled faster.
It's possible. That would help them coming off, right? Yeah. I don't know
or
that.
Or maybe that would be an interesting strategy.
Wouldn't that deplete them
Well,
faster?
Right, that's what I mean. So blocking that. So blocking
I
the
get it.
ubiquitination.
Keep
Yeah,
the
keep even
damaged
their
ones
bond
up
in
there, right?
Well, are they damaged?
Well, they're pretty sick.
No, the
They-
sodium channel.
Well, each one of the sodium channels? You mean each individual?
Yeah, so
Okay, so overall the current is down.
right. So if
We don't
if
have
they're getting
single channel.
recycled less.
I see. So just keep them up there and hopefully they won't cause an arrhythmia at 5 days?
Yeah. Well, if there's more of them.
That's a possibility. That's a possibility. Stop them from going to being sucked in.
And I also wonder.
Maybe that's what the anchor's doing, right? No endocytosis with anchorin blockade. That's a very interesting finding, an anchorin. It's a very huge protein, right? Yeah?
So maybe this is.
Okay.
Wait.
Any other-
I
don't look at these.
Based on the idea of microtubules being so important, is there evidence from maybe autopsy tissue from cancer patients that were getting microtubule-based chemotherapeutic agents versus other chemotherapeutic agents of mislocalization in this sodium
You mean
channel?
screwing up the heart cells?
Well, mislocalization of this sodium channel specifically.
I don't know that. That's a good question. I would guess that you'd have to make sure the drug didn't get to the heart. You know, and the heart's not the only thing that has microtubules, right? So there has to be something specific about the therapy to make it only go for cancer cells.
Historically, that's been chemotherapeutic.
Well, maybe there is a cardiomyopathy that comes along with too much of the agents. Is that true? Okay,
Yeah,
Doc.
very well
Good.
recognized, yeah. Yeah, I mean, it's a great point, right? You know, they get biopsies too often, so.
How long does it take in a patient to show that, or signs of it?
Everybody is different, and
Yeah.
so they do very careful monitoring. But the problem is that once you get it, there's not much to do,
Exactly.
you know? but you just want to detect it so you don't give them more. But there's nothing really.
I mean, it's amazing to me that the system is so resistant to stress, which of course an infarct is a high amount of oxidative stress, that it can actually continue to grow and these tubules get fatter and thinner and run around and change direction and still do their job, right? Rather than being obliterated. And some of the cells, they weren't there in the middle. There were some where they lost. But I don't know enough about it, except there was a paper recently about how they grow themselves. Yeah.
Have you or anybody tried to recapitulate this phenotype in a mouse?
Infarct?
Yeah, where you, I mean, infarct, yes, but the sort of, the details.
Cortisone?
Right, that you'd be able to
Actually, my technician was a fantastic surgeon on the dog, was asked to do that in mice.
Uh-huh.
And he would occlude the LAD. Now, of course, he wouldn't do any of the EP. It's entirely possible there's no cortisone surviving, because, you know.
What about if you just do like histology rather than, you know, on the intact heart and ask the question whether you're seeing the same things? Because then you could conceivably get at some mechanism.
Yeah.
See whether.
Which, you mean how what are the motors driving the proteins up
Yeah,
there and stuff
yeah.
like that, yeah.
Have you heard about SAP-70? Isn't that something that's known?
97, I
Or
think.
SAP-90?
Yeah, 97, that's more for K channels, but it's also for sodium channels. We did some work on SAP 97 and KV 1.5, and actually it's up, everything's upgraded in the infarct. Both of them.
Okay, there are no,
Thank you.
on this side, there are no? All right,
Middle
thank you,
aged people
Penny.
have